In this video, I'm going to go over an exponential application that has to do with half-life. Let's look at this example. Azithromycin is an antibiotic that is used to treat many different types of infections caused by bacteria. The half-life of azithromycin is approximately 68 hours. The first thing we're going to try to do is find the k value in the exponential model. A is equal to a sub 0, which is sometimes called a naught, times e to the kt. And let's first just look a little bit at half-life. Half-life is the amount of time it takes for a substance to decay by half. Let's look at what it means for this example, where there's a half-life of 68 hours. If the original amount of medicine administered was 500 milligrams, what that means is after 68 hours, there'll still be 250 milligrams remaining in the bloodstream. If the original amount administered was 400 milligrams, then after 68 hours there would be 200 remaining in the bloodstream. And finally, if you look at 200 milligrams, that means after 68 hours there would be 100 left in the bloodstream. Now let's look at the exponential model. In the exponential model, a naught means the initial amount. K is the growth or decay rate. For this example, we're dealing with decay. T is the amount of time. And A is the amount of the substance after time t. If the half-life is 68 hours, that means t is equal to 68. What that also means is A, which is our amount after 68 hours in this case, is going to be 1/2 the original amount, so we can write that as 1/2 times a naught. And then let's plug all this into the exponential model. Because we have a naught on both sides of the equation, we can divide and cancel the a naught. So it doesn't matter what the actual original amount of the substance was. Then we get 1/2 is equal to e to the k times 68. At this point, since we're trying to solve for something in the exponent, we can use the property where you take the ln of both sides. By doing that, that allows us to bring the k times 68 down to the front, so we end up with k times 68 times ln of e. And we can do that based on this property of logarithms. The power property states that if the log has an exponent, you can actually bring it to the front and turn it into multiplication. And here with these properties of logs, I show the generic properties of logs and also the properties that apply specifically to natural logs. And the one that's going to come in handy with these problems as well is the fact that ln of e is equal to 1. And since ln of e is equal to 1, we can simplify the equation further. I'm going to write this as ln of 0.5, just to make it easier to plug into the calculator, is equal to k times 68. So then the last step to solve for k is to divide both sides by 68. Now it's time to plug that into the calculator. ln of 0.5 divided by 68 gives us negative 0.010193, and so on. And before I move on, I want to store this value in the calculator. To do that, just click Store, and it'll automatically use the number from the previous answer. And then you can choose the button for variables, which will bring up automatically an X. And now anytime I want to refer to that number, I'll just use the button where there's the X, and it'll use this exact value we found here. When you use the store feature, not only are you saving time because you don't have to type in all of the decimals, but you're able to use the actual value instead of a rounded approximate value. Now let's look at the next part of our example. Part B. If an initial dose of 500 milligrams is given, how much will be in the bloodstream after 20 hours? Now we can use our exponential model with the value of k filled in. And for this particular example, we have that a naught, the initial, is 500, t is 20, and we're looking for a. So if we plug everything in, we get a is equal to 500 times e to the negative 0.01019 times 20. And now it's time again to go to our calculator. When we plug this into our calculator, we can do 500 times, and then remember to get to e, you would press second ln. Instead of typing in the negative 0.01019, I'm going to use the x times 20. This gives us 407.785, which I'll round to the nearest milligram, which in that case would be 408 milligrams. Now let's look at part C. If an initial dose of 500 milligrams is given, how long will it take to reduce to 300 milligrams? Again, we'll go back to our exponential model and fill in all the information that we know. In this case, we're given the initial dose of 500 means that a naught is equal to 500. Since the final amount is 300 milligrams, we're going to plug that in for a, and in this case we're looking for the value of t. That gives us 300 is equal to 500 times e to the negative 0.01019t. Divide both sides by 500. That gives us 0.6 is equal to e to the negative 0.01019t. And then to solve for the value in the exponent, we're going to again use the property of logarithms. So I'll start by taking the log of both sides. That allows us to bring down the exponent of negative 0.01019t times ln of e, which simplifies to 1. That leaves us with ln of 0.6 is equal to negative 0.01019t. To find t, we divide both sides by negative 0.01019 and then plug it into the calculator. To plug it into the calculator, I'll type in ln of 0.6 divided by x, which gives us 50.11. Rounding to the nearest hour, we'll say that it takes 50 hours for the dose to reduce to 300 milligrams in the bloodstream. Okay, now let's look at the last part of this problem. D. Assuming the original dose is unknown, how long will it take to decay to 78% of the original dose? Going back to our exponential model, we want to plug in all the information that we know. In this case, really the only thing that's given is that we're looking for when the amount is going to reduce to 78% of the original. And what that means is for that value of A, we can actually substitute in 0.78 times A naught, which means 78% of the original. And we actually don't need to know any more information because just like the first problem where we were finding the value for K, we have A naught on both sides of the equation, so we can divide both sides by A naught, which leaves us with 0.78 is equal to e to the negative 0.01019t. And we'll essentially use the same steps for solving that we used in a few other from this example. Take the ln of both sides, and then after the simplifying with that, we get ln of 0.78 is equal to negative 0.01019t. And then finally, to solve for t, we'll divide both sides by negative 0.01019. To plug that into the calculator, I'll type in ln of 0.78 divided by x, which gives us 24.37. Again, I'll round to the nearest hour. So that tells us after 24 hours, the substance, no matter what the initial dose was, would be 78% of the original. And that's it. I hope this helps with solving exponential applications that involve half-life.